In this tutorial, we will be discussing free energy and temperature. As a reminder, Gibbs free energy is the energy a chemical reaction uses to do work. It's the energy available after bonds are broken and formed to do chemical or biochemical work. It's a thermodynamic quantity that combines enthalpy, H, and entropy, S, into a single quantity. G is equal to H minus Ts. Given the following relationships, delta S of the universe is equal to delta S of the surroundings plus delta S of the system, we know that delta S of the surroundings is equal to negative delta H over T. We can then substitute that into the equation. With substitutions and multiplying through by T, then we find negative T delta S of the universe is equal to delta H of the system minus T delta S of the system, where negative T delta S of the universe equals the change in Gibbs free energy for the system. So under standard conditions, delta G of the system is equal to delta H of the system minus T delta S of the system. Let's explore these numbers a little bit further. So delta G is the Gibbs free energy change, delta H is the total energy change for the system, and T delta S is the energy loss due to the dispersal at a specific temperature. So in other words, how much more disorganized it's becoming. If it's exothermic, delta H is going to be negative, and if its entropy increases, it's becoming more disorganized, then the delta G must automatically be negative and therefore spontaneous. The product is favored. If the reaction is endothermic, so delta H is positive, and the entropy decreases, it's becoming more organized, then the delta G must be positive, therefore not spontaneous, and the reactant is favored. So those two situations were temperature independent. It did not matter what the temperature was. This did not play any value into it whatsoever. However, there are situations in which it does. If it's exothermic, meaning delta H is negative, and then if we say that the delta S is also negative, it's becoming more organized. At a high temperature, this number over here with the delta S is going to go up, and it's going to make the delta G overall be positive and not spontaneous. At a lower temperature, the delta H is going to be more prevalent, and it will be spontaneous, and delta G will be negative. If it's endothermic, meaning delta H is positive, and there's an increase in entropy, delta S is positive. At a high temperature, the delta S portion is going to take over, and it's going to be spontaneous, and delta G will end up being negative. At a lower temperature, it's not spontaneous because the delta H overpowers it, and it'll be a positive delta G. There are two methods of calculating delta G. You use the known values of delta H and delta S and the Gibbs equation. Delta G is equal to delta H minus T delta S, which is the one we're doing in this tutorial. Or you can use the tabulated values of free energies of formation delta G naught, which is what we've done in the different tutorials. So let's take a look at this. Calculate delta G and determine whether the reaction below is spontaneous. The overall reaction has a delta H of 95.7. So delta G is equal to delta H, 95.7 kilojoules per mole, minus T delta S. So T is 298. Notice it's already in kelvins, so we're okay. Now I want you to look at something right here. The fact that delta S is in joules and delta H is in kilojoules. Those have to be the same unit. So I'm going to divide the delta S by 1,000 to get into kilojoules. That comes out to be 0.1422. multiply that and subtract it, and it comes out to be 53.3 kilojoules. And since it's positive, it is not spontaneous. We'll try one more, and this one's going to be a little bit more complex because of the fact that we're going through several steps. First of all, we are given the delta H's and delta S's of all the reactants and products here. We're going to have to figure out the overall delta H and the overall delta S before we can figure out Gibbs. Alright, so let's do the delta H first. We need SO3. We only need one of them. Minus 1/2 of O2, which is 0, and 1 of the negative 296.8. So that means delta H is equal to negative 98.9. Now delta S, 256 minus 1/2 of 205.2 and 1 of the SO2s, which is 248.2. This here comes out to be 350.8. Notice once again, this is in joules. I had to get into kilojoules when I put it into the real equation. So delta G is equal to delta H minus 298 negative 0.094. Multiply and subtract that out, and it comes out to be negative 70.9. And that is how you do Gibbs free energy with the delta G is equal to delta H minus T delta S equation.